Okay.
Yeah, you don't have to apologize for the same.
Yeah. So apologies to people who are attending online. I did not correctly start the broadcast. So all you have missed, though, has been a bit of an introduction to so the learning objectives for today, which are around hypothesis testing, and then we've been just reviewing a bit more the confidence intervals, things from our previous two classes, along with the announcement, which I will talk about more about next week's exam, which is going to cover only up to today. And I will be posting an updated syllabus that shows the materials that we're covering up to today. So the margin of error is, in some instances, might be estimated using a normal sampling distribution. You use that when you had a precise value for the standard deviation. So you knew the standard deviation for the entire population. And in that case, the standard error, or the margin of error is 1.96 times the standard error for a 95% confidence interval. And if instead you estimated the standard deviation from the sample, then you instead use a critical value from the t-distribution. So you look up where the two-tailed probability is 5%, the critical value of t, and multiply that by your standard error to get the margin of error. And the t-distribution produces margins of error that are smaller or bigger than the normal distribution. Bigger. Good. You're on your feet. Right? But everyone knows that there's you know, it makes sense. There's more uncertainty in your estimate because there's uncertainty not only in your mean, but in your standard deviation. And so the t-distribution has wider tails, and your margin of error gets larger when you have to use the t-distribution instead of the normal distribution. The t-distribution has a slightly different looking lookup table as the normal distribution, but it's the same idea. The only difference is you have to know how many degrees of freedom there are in your test. And for the one sample tests that we have done so far, your number of degrees of freedom is just your sample size minus 1. So if you have n equals 10, then you have 9 degrees of freedom, and you use this row to look up the critical value of t for any given one-tail or two-tail probabilities. So this column here, one-tail probability of 0.025 and two-tail probability of 0.05 gives you a critical value of 2.26. So whereas for normal distribution, it would have been 1.96. The confidence interval from this t-distribution is that much larger. So just some key points to remember about confidence intervals, that these confidence intervals are estimated from the sampling distribution. And the estimate comes from knowing, remember we did all that talking from the central limit theorem about there are population distributions and then there are sampling distributions. And the sampling distribution tells you the distribution of sample means and upon repeated sampling. And that variability upon repeated sampling is what we use to estimate the confidence interval, because it tells us just based on random sampling alone how much that estimate in our sample mean varies. And just by using this probability here, like shown on this t-distribution, we can calculate that 95% of the time, our sample means will fall in this area if we know that sampling distribution is t-distributed. Yes?
Sorry, can you explain again how you do the t-test calculation?
This one?
Yeah.
So to calculate a confidence interval using the t-distribution, so this is the case, let's take an example of, we have a sample of size 30, like the people in this room. We measure each of your weights, and we want a confidence interval for the population average weight for the population from which we're assuming this is a random representative sample. And so in that case, if there are 30 of you, we get the average weight. That's our point estimate. That's the middle of the estimate. We calculate the standard deviation from the sample. We divide that by the square root of 30. And if we want a 95% confidence interval, that is an alpha of 0.05. I haven't really talked about alpha yet. I'll be doing that later today. But alpha over 2, that's 0.025. I need to look up this value of t for a one-tailed probability of 0.025 for 29 degrees of freedom. And to do that, I would go back to this table. Here it is, 29 degrees of freedom. It would be 2.05. So I would just calculate this s over square root of root n, multiply that by, what was it, 2.05. Multiply that by 2.05, that's the margin of error. I just add and subtract that from the sample mean. And there's your 95% confidence interval. And I can do that for a 90, this would be a 90% confidence interval. If I use the second column, this would be an 80% confidence interval. Here is a 98% and a 99% confidence interval.
The difference between using the t versus the z-score for the confidence?
So use the t whenever this standard deviation is estimated from the sample instead of known from the population. And the difference is that these values are larger than the values in the z table for the same sample size. So if from the z table with a one-tail probability of 0.025, two-tail of 0.95, that critical value is 1.96. But you see it changes. The larger the degrees of freedom, the closer it gets to 1.96, but it's always a little bit larger than 1.96. You have to get up to like n equals 500 before it actually rounds to 1.96. So that's the key thing that with the t-distribution, this is S, which means it's an estimate from the sample. When using the z-distribution, this was a sigma, which means a parameter that is known for the population. Good question. Any other questions about this? There's no rush, yeah.
Sorry, one last time. So are you using the setup with the t-value, finding it is similar to the z-value, except you just use the sample instead of the population?
Sorry, did you ask that once more?
When you're setting up the t
confidence interval?
Confidence.
Yeah.
Confidence, just trying to figure out how we find the t.
Yeah.
So is that the same setup as with the z, except we just use the sample?
Yeah, so, okay, keep in mind, like, when we get to hypothesis testing, you'll actually be calculating that test statistic, like a t-test statistic for your sample, but for confidence intervals, you don't do that. For confidence intervals, you just look up the critical value of t in this table, and that's it. I think you're looking ahead to hypothesis testing already about calculating the test statistic. For confidence intervals, the only difference, and I could have put it on the same slide here, was that when you know the standard deviation, so it's sigma, then you use your z critical value here, your standard normal. When you don't know the population standard deviation, when you estimate it from the sample, then you need the critical value from the t-distribution. And the only difference is which table you use from the back of your book. If you use software and you put your data into the software and ask it to calculate a confidence interval, it's going to use the t-table because it's going to estimate your standard deviation from the data that you gave it. I don't know how an SPSS actually to do a z-test. I'm sure it's possible, but to say don't estimate the standard deviation, use this correct value from the population instead. So yeah, if you had the true standard deviation from the population, you wouldn't estimate it at all from your sample. You would ignore the standard deviation of your sample and just use it from the population. And that reduces the sampling variability because for every sample, you have the same standard deviation. Good questions. One of the lessons from that Guess My Age survey was that a lot of you made your 50% confidence intervals and your 95% confidence intervals fairly similar to each other in size. But if your uncertainty comes from sampling from a normal population, which is not what yours did, so maybe they were reasonable, but when it does come from sampling from a normal population, that ratio between a 95% confidence interval and a 50% confidence interval is about 3. The 95% confidence interval is about 3 times bigger. And then I don't know offhand what it is for the 99% confidence interval, but it's quite a bit bigger yet. Well, let's see, for 22, 2.07 up to 2.82. Actually, it's not that big. So once again, this is a key point that this confidence interval is really an interval along the sampling distribution, that for repeated random samples, this confidence interval is where like the middle 95% of that sampling distribution is. The sampling distribution being the distribution of averages that you get when you repeat sampling from the same population. The only variability is just due to random sampling. So you'll all remember now that when you're given a data set and you're studying it, that you just have one point, you have one sample on that sampling distribution. And if you were to repeat everything, doing everything exactly the same way, you would still get different measurements and they would have a different average. It would be somewhere else along that sampling distribution. I've talked quite a bit about interpretation of confidence intervals. I hope you'll remember that, about what the correct interpretations and some of the incorrect misinterpretations of the confidence interval are. And you should know how to estimate confidence intervals from data. Yeah.
How do you explain the idea of degree of freedom?
How do I explain the idea of degrees of freedom? I tend to think about it as how much extra data you have from the absolute minimum to that you have to calculate something. So for the mean, for a one sample t-test, anything you're doing that involves calculating the mean, it takes 1 degree of freedom to calculate a mean. Because if you say you just had one data point, there's only, you can still calculate a mean, but you can't do it with 0 data points. So if you had a sample of size 1 and you calculated the mean, you would know what the value for that sample was, even if you lost it. If you had 2 data points, you have 1 more than you need to calculate the mean. So if you calculated the mean, you have 1 more data point than you is the bare minimum for doing that. And if you were to take away 1 of those data points, but you still had the mean, you could figure out again what it was. So it's, in some cases, it's not so intuitive. Like for one of the 2 sample t-tests that we'll do, it actually has like fractional degrees of freedom, and it's not intuitive anymore. But for this simple case of a single sample, you can just think about it and figure out what it is just by thinking about how many extra observations you have to calculate what you have. And since the mean has, you need 1 data point to calculate it, that then your degrees of freedom is your number of observations minus 1. If it were from 2 samples where you're looking at like the difference in 2 means, then you calculate 2 means, it takes away 2 degrees of freedom. So then your degrees of freedom is your total sample size minus 2. And the same thing like with an analysis of variance where you're calculating we'll get to that later, but if you're calculating the means or estimating the means of 3 samples, then you have your number of n minus 3 is your degrees of freedom. Let's get started on hypothesis testing. And first, why do we do hypothesis testing? And actually, believe it or not, there's debate over this in the literature. There's a lot of debate, and there have been people saying that we shouldn't do hypothesis testing at all because we can estimate confidence intervals and do things that I don't know that are maybe more informative than hypothesis testing. But I think there's a place for it, and most people think there's an important place for hypothesis testing. And a big reason for this, first, is that it allows yes-no statements. So you have a hypothesis, something that can be answered with a yes or a no, then you may want to do this, such as in this one sample context, is a population mean equal to some hypothesized value? Or in like a two-sample context, does some public health intervention cause an effect relative to the control group, or does it have no effect? Just a couple examples. Do hypertensive smoking men have the same mean cholesterol level as the general population? That's a yes or no question. Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? That's another question with a yes or no question, or with a yes or no answer. So in both of those cases, there's a no answer that says there's no difference, and then there's a yes answer that would mean there is some evidence of a difference. This was an example that I just pulled off of PubMed because I thought it was an interesting example because their statistical methods are actually kind of complex in here. It's a cluster randomized trial. They have multi-level sampling. We talked about that a little bit, like where they're sampling schools, and then they're sampling children within those schools in order to test the effect of more intensive screening for malaria in these schools, and then treatment of the malaria. And they did that because these screening programs are something that have to be implemented school-wide. You can't sort of pick 10% of the students in a school and say, we're going to screen these students and not the other ones. So what they did is randomly sampled a set of schools, applied the intervention to those whole schools, but then within each school did an additional level of let me see. So once a school term, the intervention was delivered to children randomly from select classes 1 and 5 who were followed up for 24 months. Once a school term, children were screened by public health workers using rapid diagnostic tests, and children found to be RDT positive were treated with a 6-dose regimen of a drug for malaria. So there actually is an additional randomization at the level of individual students here as I read this. But what I think is interesting about this paper is, even if you don't have the tools to do all of the statistical analysis that is performed in here, you do have the tools to interpret all of their results, which is, I think, sort of the primary goal of this course. Because if you look down here and looking at the methods and findings, let's see, first of all, there's a bunch of proportions given during the intervention period. An average of 88.3 children in intervention schools were screened at each round, so they are screening a majority of the students in the intervention schools. Right, that is why I thought that this is a cluster randomized trial. They're applying the intervention to whole schools. Around 17.5% of them tested positive by this malaria diagnostic test. 80% of children in the control and 80 more or less in the intervention group were followed up. No impact of malaria IST intervention was observed for a prevalence of anemia at either 12 or 24 months. and we haven't gotten yet to where you can interpret all of these, but you will. The adjusted risk ratio of is 1.03. We haven't covered yet what a risk ratio is, but a 95% confidence interval from 0.93 to 1.13 and a p-value of 0.621. So all you need to know right now about a risk ratio, it's a ratio of risks for the treatment group against the control group. If it's 1, then there's no difference in risk. And they've drawn here or calculated a 95% confidence interval, and that contains this no effect value of 1, meaning that there's no evidence of effectiveness of this intermittent screening for changing the risk of anemia. And then there's this value of P, which we haven't covered yet today, but we will, of 0.621. And that is a probability of observing this this result or something even a bigger effect just by chance if there is no effectiveness of the treatment. So we have risk ratio, confidence interval, p-value. We repeat that a few times. There's a couple of different outcome measurements. There's also a prevalence of B. falciparum infection, and there's also scores of classroom attention, so measures of learning outcomes. And in fact, for all of these, there's no observed effect. And what is this? But an apparent negative effect was seen on spelling scores. That's a little bit unusual. So maybe the time out of classes for the screening actually harmed their spelling scores. I don't know. But the conclusion is that in this setting in Kenya, intermittent screening and testing is, as implemented in this study, was not effective in improving the health or education of school children. Then there's some discussion of possible reasons of why that is, including possible rapid reinfection following treatment. So this is an example of somewhere where a yes/no answer is important. Want to know, is this an effective public health intervention? Yes or no? And the second take home from this is that at least by the end of maybe this class and maybe the class after, you have all the tools that you need to be able to at least read the methods, the results, and the conclusions, and understand what a paper like this is talking about and what the message of it is. Yes?
So when we're doing this, we don't have to use the double negative?
You don't have to use the double negative?
Yeah, like failed to reject the null hypothesis.
We'll talk about how to discuss the conclusion. So I don't know, what did they say here again? It is not effective in improving the health or education of school children. Yeah, it's a little, I mean, it's true. So the point is that you never prove that there's no effect. So you cannot say that there is no effect of this. All you can say is we didn't observe any effect. So this is maybe a little bit sloppy language here. And it's a good point, even before we've covered hypothesis testing, to point that out. I mean, I think this is, as long as you know in your own minds what it means to fail to reject the null hypothesis, which we'll be talking today, then then you won't be, you will catch little bits of language like that, and you'll know how to interpret it. The logic of hypothesis testing is basically this, that your observations come from one of two population distributions, and before you do your study, you're not sure which. It's either a usual distribution that you've seen in the past, or it's something new that has been induced either by an intervention or because it's a specific group of people. This is sort of a classic example of what this inference means. Like you have a handful of beans, and just a few of them are white. So they're mostly like brown beans with like 2 white ones. You have a bag full of almost all white beans. Then this handful did not come from this bag, because even though it's theoretically possible to find that many brown beans in this whole bag, if you just picked it out randomly, you're going to get a proportion of white beans that's approximately the same as the bag. So in that case, you would reject your null hypothesis, or say that probably these beans were taken from some other bag, because the distribution is just too different. That's sort of all there is to hypothesis testing. Any questions about that? I mean, if you understand that, then you're going to understand a lot about hypothesis testing. And this also gets back to your question of, if you see that in your handful that only a few of the beans are white, that doesn't mean you haven't proven that it was taken from this bag. You can only say that it's consistent with this bag. You haven't disproven that it was taken from that bag of beans. So sort of like, I don't know, catching a kid with a cookie, and you have a jar of chocolate chip cookies, and the kid has a ginger snap cookie. Well, it didn't come from that cookie jar. So you reject that hypothesis that it came from that cookie jar. If it is a chocolate chip cookie, you haven't proven that the kid took it from that cookie jar. You're just saying they could have. It's consistent with what's in this cookie jar. Yeah.
So it's like observational?
It can be observational or experimental.
Right, like that's what you see. Like in your example, right? There's a cookie jar, there's a bunch of chocolate chip cookies. The child has a cookie that's not chocolate chip. Yeah. So all you're doing is stating what you see. Like it's possible that it came from that jar, but it's possible that it didn't.
You're stating whether it is, you think it is probable that it came from that cookie jar. So you have a cookie jar that has like 100 chocolate chip cookies and 1 ginger snap, and this kid has a ginger snap cookie. If they just kind of reached in and randomly took one of the cookies, it's unlikely that they would have gotten a ginger snap. So you could conclude it's more likely that they got it from somewhere else. So you reject that hypothesis that it came from this cookie jar. Whereas if they had a chocolate chip cookie jar, you'd say, well, I can't reject it. It could have come from this. It could have come from this jar. I've never used this example before. I don't know where it came from.
It worked.
Yeah. Yeah, maybe I like it better than the bean example. This is one you see in a lot of intro textbooks, but this is another common analogy used, the courtroom trial, where a defendant is considered not guilty until guilt is proven. And in this example, that would be what we call the null hypothesis, would be not guilty. So in the absence of any evidence, you would accept that null hypothesis. Then the prosecutor tries to prove the guilt, and if they manage to do that, they make it seem so improbable that that null hypothesis is true, then they succeed in convincing the jury of an alternative hypothesis we call HA or H1. And that alternative hypothesis is accepted only when there is enough evidence to reject the null hypothesis. So null hypothesis is always the hypothesis of no difference. It's the one that you start with and the one that you would accept in the absence of any evidence. And then in the face of evidence that makes that improbable, then you go towards the alternative hypothesis. So in the case of the, well, I don't know, I'm not going to go back to the cookie jar because it's kind of different from, from this example. But in the courtroom trial, I can also introduce here, so there are two different right decisions. I'm putting on the columns here sort of the truth, something that as a juror or as a researcher you don't know, but you kind of assume that the truth is out there, that yeah, this defendant is either truly not guilty or truly guilty. You don't know what it is in advance, but you know, either they did it or they didn't. And then in the end, you have to submit either an acquittal or a conviction, and maybe you get that right, and maybe you get it wrong. And there's two kinds of ways you can get it wrong. The first way is if the null hypothesis is true, so you have an innocent defendant and you deliver a conviction. That is what is called a type 1 error. That's when you think you have good evidence and you reject the null hypothesis when in fact you should not have. And then the second kind of wrong decision is the so-called type 2 error, where in this case the defendant is guilty, but you deliver an acquittal. So there is, the evidence is out there, but you didn't have it. And so you stay with the null hypothesis. Another example of type 1 and type 2 error. The false positive is another word for type 1 error, where the doctor says the male patient here, you're pregnant, or the type 2 error, you're not pregnant, for the obviously pregnant woman. Now, there is a relationship between confidence intervals and hypothesis testing, and there are limitations to that relationship too. In the one sample confidence interval and hypothesis test, which is what we did the last couple of weeks with confidence intervals, we constructed a confidence interval around the mean of a single sample. There is a direct relationship to hypothesis testing. So we're calling that for a 95% confidence interval, I'm just for convenience talking about the z-test here. It would be the same for the t-test as well. We find the values of z that contains 95% of the probability, which was 1.96, and we add that and subtract that to the sample mean. So remember the z-score was like the sample mean minus like the mu0, a hypothesized sample mean, divided by the standard deviation. In the confidence interval setting, we set that population mean equal to the confidence interval so that z is 0 at that mean, and we take the values of z at plus and minus 1.96 to construct a confidence interval. Now, in the hypothesis test, we need to have a null hypothesis. And that can be something like, in the one sample test, it would be like some hypothesized value for the population mean. That would be what was expected based on a census or based on some much larger sample. And z equals 0 corresponds to a sample mean equal to that hypothesized mean. So in this case, z would be the sample mean minus this mean under the null hypothesis divided by the standard deviation. In doing that, we would calculate a value of z, and then we would reject null hypothesis if it is outside of this critical region. So the key thing is that this critical region is in the same place for both of these tests at 1.96. And it turns out that that means that you can use either of these interchangeably to decide whether to reject your null hypothesis or not. I'm going to make that more explicit now with a 5-step program for hypothesis testing. The first of these is to state your null hypotheses, and I want you to pay close attention. I'll give you some examples here, and just do this in a formal way, not too much writing about what they are. Just use a formula or state it in a really minimal, formal way, exactly the way we do it here. It's the best way to avoid trouble. You'll specify a significance level, that is represents the amount of confidence you want to have, if it's a confidence interval, or it's your type 1 error in hypothesis testing, and we call that alpha. You then do your study, take a sample of size n, compute the test statistic. It will be calculated in the same way, whether you're going to use a z distribution or a t distribution. From that, you can determine a p-value. If you're using software, that's what you will get as a p-value, or you can also just compare this to a critical value in your table, and then decide whether or not to reject the null hypothesis. And finally, as you saw in that paper, state the conclusions in terms of the subject matter. So let's talk about them in a little more detail. Formulation of the null alternative hypothesis. So the null hypothesis states that there's no difference from the past, or no difference from what one would expect from an ineffective intervention, a treatment that has no effect, or let's say a portion of the population that is exactly the same on average as the rest of the population. So it posits a distribution for the population from which our sample was taken that reflects no change from the past or from our control or our reference group. And if that null hypothesis is true, then any difference that we see between our sample test statistic and that sort of hypothesized difference is only due to sampling variation. So, you know, if you expect like a population mean of 211 units of cholesterol, and in this group, it's 210. Well, if the null hypothesis is true, then whatever that difference is between our sample mean and what we expected from the population is just due to random sampling variability, not to anything else. That's what the statement of the null hypothesis is. It says that the discrepancies that we see from that null distribution for the known population is only due to sampling variability. So that's actually a first point of confusion, I think, because we write this down in terms of like mu equals something, or in two samples, it's like mu1 equals mu2. But you know that in samples, if you take two samples, they're never exactly the same. But that doesn't matter. It doesn't have to be that the sample means are exactly the same. It means that the population means are the same. And the differences that you see in samples are due to sampling variation. And then the alternative hypothesis states that there is a real difference between the distribution of our observed data and the distribution that we hypothesized under the null distribution. And if that is true, then the observed discrepancy between our observed data and the null hypothesis distribution is not due to chance sampling variation, but to some systematic difference. So if the null hypothesis seems unlikely given the data, then we're going to instead accept this alternative hypothesis. But we're only going to accept that alternative hypothesis if there's evidence. That is, that it seems very unlikely that this is a result of the null distribution. So in that example of cholesterols, if the population average is 211, the sample average is 210, that's very close. If there's, assuming that the standard error is not tiny, then maybe that's consistent with a population average of 211. Whereas if we observed 180, then that's starting to seem less probable to have come from a population where the average cholesterol level is 211. And the further it is from that population average, and the smaller the standard error, the less probable it becomes that your sample was drawn from that null distribution. And I like you to write these down in a really simple, really formal way, just like this. So here's a set of null hypotheses for a so-called two-sided test for the mean of one sample. And I call it two-sided because we're going to use both tails of the sampling distribution, the Z distribution or the T distribution, but this is just for the mean of one sample. So it's the null hypothesis is that the population mean from which we draw our sample is equal to the population mean for our reference population. And the alternative hypothesis is just that this population mean from which we draw our sample is not equal to our reference population, the mean from our reference population. So these are really simple. If I ask you on the test to state a null and alternative hypothesis for the mean of one sample, you can just copy this and then say what what mu and mu zero are. Like if you know, mu is the average blood pressure for smoking hypertensive males, and mu zero is 211 milligrams per 100 milliliters, and that's what the reference average blood pressure is. Then you've got a right answer. But I can tell you from many past semesters that generally lots of students get carried away and write a bunch of stuff about the null and alternative hypothesis, and it's a case where really less is more. You know, you need to say enough so that, I mean, you know, don't just put this and nothing else, because, you know, I want to know that you know what these things mean. So, you know, you can write this and say what mu and what mu zero are, but then that's enough, and that shows that both that you know what populations these correspond to, what this value is, if there is one, and importantly, and this is a really common mistake, that these are population averages. They're not sample averages. It's a really common mistake to make this like X bar, or like the, you know, just say like the sample average, or somehow make this about the sample and not about the population. These are about population averages. All of our hypothesis tests are about population averages. Yes?
So two-sided, you're saying we're looking at the relationship, whether it increases?
Right, so my two-sided here is actually referring to the alternative hypothesis, in that the population of interest, the mean of the value from it, can be either greater than or less than the reference mean. That's what I mean by two-sided. So this is another example of a correct statement of the null and alternative hypothesis, where I just put the actual numbers here. This is a good way to state it as well, rather to save you having to put mu zero and then say below what mu zero is. The null hypothesis is that mu, which is the average, the population average, blood pressure for smoking hypertensive males, is the same as that of the general population, which is 211 milligrams per 100 milliliters of blood. And the alternative is that average blood pressure for smoking males is not equal to that of the general population, either greater than or less than, for a two-sided test. Two samples will be primarily in the next class, but just to give you a preview, for two samples, we're comparing the means of two populations, which may have the same mean for whatever we're measuring under the null hypothesis, or they might be different under the alternative hypothesis. It's just an alternative way of equivalently stating the alternative hypothesis, that the difference between the two population means is not equal to 0. And we can also write down null and alternative hypotheses for proportions. So in that example of the intermittent screening and treatment for malaria, their null hypothesis was that the proportion of, they had several outcome measures, but for one of them was the prevalence of anemia. The null hypothesis is that the prevalence of anemia under the normal sort of standard approach is exactly the same as the prevalence of anemia in schools receiving the intermittent screening and treatment. And these are population proportions. So this would be a hypothetical population of schools that are all receiving the intermittent screening and treatment, and this would be the existing the population of students in schools that are not receiving that treatment. And the null hypothesis, or the alternative hypothesis here, is that these two prevalences are not equal. And you'll notice that I did not make this like an inequality that would have made this into a one-sided test. My alternative hypothesis is not that the prevalence in treated schools is less than in control schools. There are very limited situations where we would actually use a one-sided test. In the very few situations where you actually would use a one-sided test, your null and alternative hypotheses look like this, where the mean value in your population of interest is less than or equal to the mean under the null hypothesis, and an alternative where this mean is greater than the null mean. So the null hypothesis always contains an inequality, or sorry, always includes the equality. So mu might be equal to mu0 or less than. That equal to never goes with the alternative hypothesis, always with the null hypothesis. So the null hypothesis must include no difference. And in this one-sided scenario, it can also include an inequality, like less than. This goes also for means of two samples. And of course, this inequality could be in either direction, greater than or less than. That choice depends on context. And it's a bit controversial because one-sided tests give you smaller p-values. If you have put your inequality in the right direction, like with, say, that malaria trial, if you made your alternative hypothesis only including that the prevalence of anemia in the treated group can only be less than in the control group, then you actually cut your p-value in half. So you make it easier under random sampling to reject your null hypothesis and to, in that example, assume that or conclude that the treatment is effective. And so for that reason, it's controversial because it can be unconservative. It can lead you to make type 1 errors more frequently. And as a result of that, two-sided tests are really the norm. And any one-sided test not only must be clearly justified in advance of the test, but there should be no reasonable possibility of another alternative hypothesis. So in that malaria study, you know, who knows? You can't rule out the possibility that this intermittent screening in malaria could somehow increase the prevalence of anemia. Maybe it leads to I don't know, riskier behaviors or something, like some sort of compensating behavior. You can't rule it out. And unless it's completely impossible, you need to include all possibilities. Because in the simple null case of no effect, you'll double your type 1 error rate by choosing a one-sided test. The only case where one-sided tests are really accepted are in so-called non-inferiority trials. That's where you have, for example, a well-established drug that you know it's effective, and you want to introduce, let's say, a generic equivalent of it. And you want to test the effectiveness of this generic equivalent. There is no reason to expect that that generic equivalent is better. It's just a copy of the drug. All you want to know is that it's not inferior to it. And in this case, if it's inferior, you actually want a more sensitive, more powerful test to determine that it's inferior. So it's actually good that it's easier to reject that null hypothesis. So in that case of non-inferiority tests, one-sided or one-tailed tests are the norm. But other than that, it's two-tailed tests. Step 2, specifying the significance level alpha. It's the acceptable type 1 error probability of the test. So the probability of concluding that the alternative hypothesis is true when it's actually false, when the null hypothesis is true. And typically it's taken to be some small value like 0.05 or 0.01, very frequently 0.05. And it plays the same role as the error probability in confidence intervals. So in confidence intervals, it was 1 minus alpha, was for like a 95% confidence interval, means you have a 5% probability of being wrong about the correct population mean being in that interval. Here, it's the probability that under a true null hypothesis, you reject it anyway. So this is the type 1 error rate, and it's something that we set in advance of doing our analysis in order to control that type 1 error rate. Step 3, you're going to keep using this, by the way, as we do more and more tests. You'll use these same tests, is calculating the test statistic. And that is something that comes from our sample, and it is the statistic on which our test will be based. And it's the thing that measures the difference between our observed data and what we expect under the null hypothesis. It's something that tends to be small. If the null hypothesis is true, and larger values make the null hypothesis less and less plausible. For a single sample with a known population mean, we calculate the z statistic, which is the sample mean minus our mean under the null hypothesis, divided by the standard error. If this standard deviation were estimated from the sample, we would calculate it in exactly the same way, but we would call it a t statistic, which is what we normally use in practice. So this test statistic, we're then going to interpret as one observation on a sampling distribution. And based on where this sampling distribution is something that, again, we don't know. We don't observe it directly, but it's just a result of our null hypothesis. Our null hypothesis says what we think the population mean is, what the distribution is. In this example, we have a normally distributed measurements and either a normally distributed sampling distribution or a t-distributed sampling distribution. our next step, the p-value, is just going to be the probability in the tails of this distribution of observing our test statistic or something more extreme than it. And so that fourth step of calculating the p-value is done under the assumption that the null hypothesis is true. And under that assumption, we know what the distribution of that test statistic is. And it's just a calculation of the probability of observing our test statistic or something even larger under a true null hypothesis. So in the example of the cookie jar, it's the probability that that cookie would have been drawn from this jar under the assumption that it was drawn from that jar. So our one sample hypothesis test and all hypothesis tests involve calculating a test statistic for our sample, which is one observation from a sampling distribution that has a known shape under the null hypothesis. So part of the importance of forming that null hypothesis is that it gives us a theoretical distribution that we can use to calculate the probability of our sample coming from that distribution. And then finally, step 5 is to accept or reject the null hypothesis. If you calculate a probability that is less than our significance level alpha, then we reject the null hypothesis, we accept the alternative hypothesis. If the p-value is bigger than alpha, then we consider that insufficient evidence to reject the null hypothesis, and we stick with the null hypothesis for lack of evidence to reject it. And then finally make conclusions about the question at hand in the context of the study. So going back to this example of the intermittent screening and treatment for malaria, let's see, first of all, what is the outcome variable? There were several of them. What was one of them? A little bit small to see now. Although I've talked about them, what was one of the outcome variables? Yep.
The confidence interval?
No, yeah. Outcome variable is like a measurement, something you measure. Sorry?
Risk ratio?
No. No, risk ratio, confidence intervals. I mean, these are statistics. These are like, these are estimates we're making about something. Yeah.
Anemia?
Sorry?
Anemia.
Anemia, very good. Anemia is one of the outcome variables here. There was anemia, there was sustained attention. Second outcomes were malaria, parasitemia, and educational attainment. Outcome variables are the variables of interest, and they're variables. So just, you know, like all of the variables we learned in the first couple of classes, it's things like those. So in this case, anemia, educational attainment. Let's say for anemia, what are H0 and HA? This time you'll have to say it in words. Sorry?
So there's no difference. There's no difference between an anemia before the intervention and after the intervention.
Yeah, it's maybe just to make it like absolutely explicit. Yeah.
H0, and in the null hypostasis, there is no difference in the prevalence of anemia between the control and the treatment group. While the HA states that there is a difference between the prevalence.
Yeah, the only thing I would be careful there is you said in the control and treatment group, which kind of to me sounds like sample. So just to be really clear, the null hypothesis is that intermittent screening and treatment has no effect on anemia prevalence in the population. And the alternative hypothesis is that it does have an effect on anemia prevalence in the population. So just be careful to state very clearly that your null and alternative hypotheses are about the population prevalence or the population mean, not about the groups or the sample groups.
Will that be a case where we put H0 is not equal to H, like the null is not equal to what was actually hypothesized?
Yeah, let's see if I can write it down. So it would be like H. I have a blue marker. None of these are visible, are they? Okay. I wonder if I can write on here. No, not really. I have no way to write. So if I were writing it out here, I would say H0 colon, actually I did it on a previous slide, like capital P subscript C equals capital P subscript T, where capital P subscript T is the prevalence of anemia among treated children, and capital P underscore C is the prevalence of anemia among untreated children in the population. What significance level alpha was used here? They don't actually explicitly state it, but they do give a 95% confidence interval, which implies to me that alpha is 0.05. What is the p-value? They gave several of them, 0.621, 0.953. None of those are less than 0.05, which is why they did not conclude that, that this treatment was effective for any of their outcome measures. So H0 was not rejected because the p-value is greater than alpha, and it was reported in that final sentence where they said that the treatment was not effective, but as someone pointed out, it would have been more accurate just to say that there is no evidence that it was effective. It could have had some very small effect that that we just didn't have a large enough sample size to observe. But there was no, any observed effect was consistent with the null hypothesis. So here's an example. Cholesterol levels are normally distributed with a mean of 211 and a standard deviation of 46 in men in the United States. And then there's this question, do hypertensive male smokers have the same mean cholesterol? So step one is to write out this null hypothesis, H0 colon mu equals 211 milligrams per 100 milliliters, and the alternative hypothesis, HA colon, that mu is not equal to, where mu is the mean cholesterol level for hypertensive men. Step two, let's set alpha equal to 0.05. In step three, we've done our experiment. Let's take a sample of 25 hypertensive males and say that the average cholesterol we measured is capital X, or capital X bar, what would we conclude if X bar is equal to 195? So recall, so our Z statistic would be the absolute value of 195 minus 211, that's 16 divided by 46. I don't know offhand, but that's about 0.33. I can tell you, well, wait a minute, I didn't calculate. So the standard error is 46 divided by the square root of 25. So 46 over 5, that's about 9. I wish I could write this down here. If I can. So the standard error equals 46 over 5, which is about 9. Uh, 195 minus 211, that's 16. 16 divided by 9, what is that? It's 1.7. So that is less than a critical value of Z of 1.96, so we're not going to end up rejecting the null hypothesis here. In this second one, it's, let's see, 227 minus 211, that's 16 divided by 9. I think it's the same thing. It's still not quite big enough to reject the null. Yep.
Sorry for all the questions.
That's okay.
So we can look at the Z-score and use that to reject. You said the Z-score of 196.
1.96. That's the critical value of Z for a two-tailed probability of 0.05. So if in this one sample Z test, if we get a value of Z more than 1.96 or less than 1.96, then we would reject the null hypothesis.
We don't see other populations. Otherwise, we look at
Did that answer your question?
I thought we were using P to figure out if there was significant difference.
Yeah, so I'm taking a bit of a shortcut here because I remember off the top of my head that critical value of 1.96. So if to get a p-value, we actually have to look it up in that Z table and find for 1.6 or whatever that is. We can look up that probability in the Z table. So I think I've actually done that here for a Z value of minus 1.74. That probability under one tail is 0.041 and under two tails is 0.082. So the p-value is 0.082. So for the Z test, we can estimate a p-value by looking it up in a table. For the T test, you're only going to be able to do that with the software. The table is not precise enough to calculate the actual p-value. And I wrote that down before that we calculate the p-value because almost always you're going to use software, you're going to get a p-value, you're going to compare it to alpha. This is a bit of a relic of like using tables and things that you don't necessarily have to calculate a p-value, you just reject or not, but it's not the usual situation. And the p-value is actually the same for 227. It was just a positive z-value instead of a negative z-value. So the point there was just under these two-tailed tests, the p-value is the same for if you're a certain amount above the null mean as opposed to below the null mean. It's only the absolute value of z that matters. Mm-hmm.
Wouldn't it be rejected because it's 0.08, it's higher than 0.05?
It's not rejected because 0.08 is higher than 0.05. Yeah, that's important. So this is the probability of observing a mean cholesterol that is this far from the expected amount by chance. So the smaller that probability is, the less likely we were to observe this mean cholesterol by chance. So if we have a p-value of 0.001, we're going to reject the null hypothesis because it was really unlikely to observe it by chance. If we have a p-value of 0.08, we're not going to reject the null hypothesis because there's still an 8% probability that we could have observed this by chance. Yeah, great question. It's actually often a point of confusion when people talk about, like, sometimes people will say a large p-value to mean highly significant, and it's a small p-value. I like to say, I often just refer to like more significant or less significant. But when I do say a small p-value, I mean that it's a small value and it's more significant. So step 5, we decide not to reject the null hypothesis. We conclude that the data do not provide significant evidence that the population mean cholesterol level for our target population, which were hypertensive males, is different from the overall population of US males. So does this mean that we're 95% confident that the null hypothesis is true, that the cholesterol level of hypertensive males is the same as for all males? No.
We're not doing individuals.
We're not doing individuals, and we're not also not our alpha level is our type 1 error rate. So it tells us that we could observe this the cholesterol level that we observed, and it is consistent with the null hypothesis. We would only make a false rejection 5% of the time. But it's not related to the confidence in H0 being true. Because you should remember that one way to fail to reject your null hypothesis is just by not collecting enough evidence. So you collect some very small sample size and fail to reject your null hypothesis. That doesn't increase your confidence in it does not give you a probability of the null hypothesis being true. I'm running over time, so I think I'm going to skip over example 2. This is kind of a silly example anyways, because we would never do a one-sided test in this scenario. But I am going to tell you about testing proportions for large sample sizes. We've covered this normal approximation to the binomial distribution, where you can calculate a z-value in the same way as with a continuous variable, just using the proportions. and you can estimate a standard error also using your observed proportions, and then you can use these to perform a hypothesis test in the same way. So finally, merging hypothesis testing and confidence intervals, you can decide whether or not to reject the null hypothesis based on your confidence interval. You can check your confidence interval and it contains your hypothesized null mean, then you don't reject H0. If it does not contain the null mean, then you reject null hypothesis. So in that cholesterol example, if we had built up a confidence interval for this sample, it would have been the standard error was 46 over the square root of 25 multiplied by 1.96 is the sample mean plus or minus 18. So with 200, the 95% confidence interval is 182 to 218, which contains 211, so that's okay with the null hypothesis. With 190, it no longer contains 211, so we reject the null. For 239, it again no longer contains the null value of 211, so we again reject H0. Those are equivalent. You would come to the same decisions every time using either approach. And we can do that for one sample tests, but for the two sample tests that you'll do after the exam, it's not the same thing. Two overlapping confidence intervals does not mean that you might still reject the null hypothesis. So if you have two non-overlapping confidence intervals, certainly you would reject the null hypothesis, but if they're overlapping, you might still reject the null hypothesis. So you come to different decisions in those cases. And if you want, there is still an equivalence, but what you have to do is build a single confidence interval for the difference in those two means. And if that difference in means contains 0, then it's consistent with the null hypothesis. So remember I showed you this little table before where there were the two no error possibilities and the two types of error. Type 1 error, which we control with this by setting this value of alpha. That's where the null hypothesis is true, but we incorrectly reject it. And the other type of error was the type 2 error, where the null hypothesis is false, but we fail to reject it. That is called beta, or type 2 error. And then one of these correct cells where the null hypothesis is false and we correctly reject it, that has a special name, and it's called power. And power estimation is an element of designing studies where you you have a hypothesis that there is some difference between control and treatment or between two populations, and you try to design a study that has a sufficient sample size to be able to observe that difference and reject the null hypothesis with a certain probability that's called the power. Just some basics ideas about power, which will continue, is that it's related to these other concepts. So the bigger the difference there is, so the bigger difference between two means, or the bigger difference between our mean and the population, like the further, the higher the cholesterol level is of hypertensive males, the more your power increases or your type 2 error decreases. That is, the easier it is to see a true difference. the more the population variability decreases or your sample size increases, that also increases your power. However, the type 1 error rate is something that you remember you fix in advance. So it's independent of mu1. It's something that you decide on. And generally, when you design a study, you want the power to be as high as possible within the limitations of your resources. Okay, so final slide here. If we reject the null hypothesis, is the probability that H0 is true equal to 1 minus alpha? The answer is no. We do not estimate the probability that the null hypothesis is true. All we estimate is alpha, which is the probability of observing our sample, given that the null hypothesis is true. So the p-value is the probability of observing our sample under the null hypothesis. Failing to reject the null hypothesis, even though the alternative is true, that's the type 2 error. And 1 minus the type 2 error is called the power of the test. And a couple final points about statistical significance. It is not the same thing as practical significance. So it is possible to have a statistically significant result that in practice is not meaningful. You have very large sample sizes. You could determine that one group, their cholesterol level is significantly different than the other group, even though that difference is only like 1 unit. And like health-wise, it makes no difference, but you can detect it significantly. So small differences in means might be statistically significant, but not practically significant. Any questions before? So the second exam will just cover the material since the first exam. So the last several classes that we had since the first exam. You should still know the stuff from the first exam because, I mean, you will need some of it just for this materials, but it focuses only on the stuff since the first exam. The rules are the same. It's an open book exam. It will be in a lot of ways similar to the first exam, just on different materials. I think we will try to make some practice questions available to you in the next couple of days, unless you want to just have the homework be practice questions. And we have some practice questions available, I think.
I have some I posted Tuesday.
Okay, just have to remember to take out the 2-sample hypothesis testing stuff from them. Any other questions about the exam? Sorry? Today's material is also on the exam. Yeah.
The next exam is next week.
What's that?
Is the next exam on next week?
Yes, it's next Monday.
Next Monday.
Sorry, Tuesday. I got my days of the week mixed up. Next Tuesday, regular class time. Yes. Same format. Yeah. All the same rules, same format, same length of time. Probably similar level of difficulty. It's going to cover less material, but Yeah, it should be kind of a similar level of difficulty. One other thing I have to let all of you know, I'm going to be, in the next couple of weeks, having to take medical leave for the rest of the semester. I've been diagnosed with an oral cancer, so Tony is going to be taking over the course for me probably after the exam. So I'll be, I don't know exactly when yet the treatment's going to start for me, and I'll stick around for as long as I can. But I won't be able to finish the semester with you, so my apologies for that. But with that, I'm going to call it a lecture and let you take 5 minutes break and then let Tony take over.